So, good afternoon, ladies and gentlemen. It's my great pleasure to introduce Giuseppe Tomassetti from Roma Tre University. He's a quite frequent visitor in Prague, and I think even more often he gives a talk here at the seminar, and he always has very interesting topics. And now the topic is a little bit different from what I announced in the email, but there is eyebulb, and I think this is important part of the topic. So.
Okay, thank you very much, Martin, and thanks for letting me give this talk at the seminar, at the Nečas seminar. And yes, it's true. I've been.
Okay.
Yes. I've been here several times since I met with Tomas, and then a collaboration started also with Martin and with Stefan and all these nice people here. And but today, so this is different from the type of seminars I've given before. Those I've given before were more connected to mathematics. This is more connected to modeling, and with a specific reference to a biological application, which is the study of how can I minimize this without doing too much harm. Okay. It's related to a biological problem of the vibration of the eyeball. So, you know, the vibrations of the eye. And where does it come from? Actually, the proposal of doing this work came from this guy, Rodolfo Repetto. He is quite famous in the biomechanics of the eye community because he's done a lot of work with applications of fluid dynamics. Is from fluid dynamics to problems involving the mechanics of the eye. And one of these papers, several of these papers are concerned with the dynamic properties of the eye. So he studied essentially problems where the eye is modeled as a spherical rigid solid containing a viscoelastic material. And he wanted to study what were the vibration properties of this material. And this was related to one may wonder why you want to do that, because the dynamical properties of the eye seems to be quite important as far as biomechanics questions are concerned. For example, it's known. Let me show you. These are schematics of the eye. So as you can see, the eye is essentially can be thought as a spherical shell, almost spherical shell, containing two chambers. This is the anterior chamber, and this is the posterior chamber, the largest one. And in this talk, I will focus mostly on the posterior chamber, which essentially can be thought as a structure made of elastic shell, which is the sclera, this one. And this elastic shell encapsulates a viscoelastic fluid, a viscoelastic material. So the vitreous humus has viscoelastic properties that are well known and are thought to be important to prevent eye injury. So it provides not only support to the eye, but it also provides protections from injuries, impacts, and so on. And this is because it's essentially a viscoelastic material. If you look at the composition, this is made 99% by water, plus a double network of collagen fibrils and hyaluronic acid. And this gives the functions of the vitreous eye are essentially to provide mechanical support to the eye to prevent this from collapsing, of course. And in addition, it's thought to be that nature has designed the properties of this material so as to provide protection and shock and vibration analysis absorption. And these are the properties that can be attributed to the rheological properties of the material. So the study of the intrinsic vibrational properties of the eye would provide information about its damping characteristics. So coming back to the previous slide, so Rodolfo came to me. So what happened? I have to Control L. So came to me and asked whether it was possible to modify his model to incorporate deformability of the sclera. So in his previous studies, he had considered the sclera as rigid. He wanted to see what was the effect on the vibration properties of taking into account the deformability of the sclera, which of course is not perfectly rigid, okay? And in fact, we found that this kind of investigation could have a potential application in acoustical tonometry. So some of you know that the eye is a pressurized organ. And the physiological pressure for healthy subjects is around 2 kilopascals, which is equivalent to 15 millimeters of mercury. This is the standard number for ophthalmologists, okay? But sometimes it happens that people develop high pressure in the eye, and this can lead, as some of you know, to pathologies like damage to the, essentially damage to the retina and to the optic nerve. And so it would be important to monitor with a certain, on a regular basis, the changes of pressure of the eye. And what is known is that the pressure in the eye can change quite relevantly, even in the same day, within the same day. We have oscillations throughout the day. And it would be nice to have a device that the patient can use by himself or herself to measure the pressure at different hours of the day. Okay, but this is not possible nowadays because I think some of you have tried the measuring the eye pressure, probably with AirPad. Most of you, has anyone tried that? Okay, it's not a pleasant thing. And the mechanism to pressure, the way to measure pressure in the eye is based on the idea that you impose a displacement, you apply a force, you measure the displacement, and from the relation between force and displacement, you can infer the internal pressure on the eye. But of course, this way of measurement presents a lot of unknowns because the result depends not only on the internal pressure, but also on the mechanical properties of the cornea, which is thickness and rigidity and so on, which are properties that can change from one individual to another. And moreover, within the same individual, change with age. So in fact, I was talking to an ophthalmologist who confessed that in fact doctors are not completely aware of what they're measuring. We don't know what we are measuring. We just know that the machine gives that number, and this number should be to within some range. But the problem, of course, is that this kind of measurements cannot be self-administered. You cannot do this on your own. Okay, you need a medical operator. So it would be nice to have a simpler device that can perform this kind of measurements. And so, suggestions. So this is an idea that goes back to the 90s. So suggestions have been made that it would be possible to infer the pressure of within the eye by measuring its resonant frequencies. And I don't know if someone has ever tried to inflate a balloon. You can notice that the proper frequency of the balloon changes as you blow it. And in fact, what you expect is that the higher the pressure, the higher the resonant frequency, the proper frequency of the system. So the idea is that it should be possible to detect changes in the intraocular pressure, IOP, by a shift in the resonance. Okay, but the problem that they pointed out that it's quite difficult to obtain an expression for the resonance of a spherical fluid field, damped elastic sphere in terms of internal fluid pressure. So they acknowledge that this was a problem. And but there are people who have been investigating this issue with many different methods. People have used experimental methods. So ex vivo experiment of, for example, on samples of porcine eyes, which are quite similar to the human eyes. Also ex vivo experiment on human eyes. They also made numerical simulation with full finite element codes describing both the shell and the internal fluid. They have made also experiments. So these experiments usually were made by inflating the eye with water, with a solution of water and salt, for example, and measuring how the frequency would shift according to the pressure. And what you can notice from there are three numbers in each row, because essentially these are the lowest mode. If you know spherical harmonics, you know that the lowest spherical harmonics has three modes. Okay, and as we shall see, vibration in the eye can be described analytically by spherical harmonics, and these three are the lowest modes. And if you notice these lines, you will see that these data are quite scattered. And the reason is multiple. I mean, because from individual to individual, mechanical properties may change, and so on. So you see that the range is from 34 Hz, as low as 18 Hz, to as much as 450 Hz. Okay, so Rodolfo came to me because he thought that I was an expert in shell theory, which was not quite true at the time, I have to say, because I did some work on that, but I had been working more on plates, I have to say. So the first thing I did was to look at the literature and see what was available. And for example, this is a paper where axisymmetric motions of spherical shells filled with fluid are studied in vibration. And this paper was in fact devised for another application, which was the vibration of the skull, in fact. But it's quite similar to the eye. And of course, when I was looking at those equations, I found a very big difficulty, because it's not easy from a mechanical standpoint to interpret all these terms. So you don't have an idea. I mean, someone who knows mechanics would be in trouble in saying what are these terms coming from if you look at the equations. And I also found another paper where, again, sorry. I also found another paper where vibration were studied for a pressurized spherical shell. And this is quite recent, in fact. I mean, it's not too old. So something happened with the, okay, so 2015. And here, as you can see, there is an elastic shell. And these are the material properties. So Young modulus, density, Poisson modulus. This is studied in axisymmetric motions, which means that the displacement field has two components. The normal component U, this one, and another component which is V. V is one of the two tangential components that is non-zero for axisymmetric motions. And in this paper, the effect of the internal pressure is incorporated in the equations, I would say, in I don't know. I mean, they just added the effect of pressure in using an ad hoc argument. Okay, the derivation was not so systematic, I have to say. So they took the standard equation for linear shells and they added the effect of internal pressure and the pretension that comes from internal pressure just by, I would say, a very ingenious ad hoc argument, but still an ad hoc argument. It's not a systematic derivation, and this I didn't like. Okay, so I said, okay, is it really necessary to use coordinates to write the equations that govern elastic shells? And this is not true. There are examples from the literature where people have studied that without using coordinates at all. The oldest paper that I'm aware about, it's this paper by Gertin and Murdoch. Murdoch at the time was a student of Gertin. And in this paper, 1975, they developed a theory of elastic surfaces, okay? But in this case, the type of material the type of structure that they studied were membranes, no bending effects. So this was not enough for me, because I thought at the time that bending would be important. And then I found another paper, which is relatively recent, 2013, by Miroslav Shihali, who was compelled to was as well unhappy as I was with what you find in the literature for the equilibrium equations for the elastic shells, and he derived those equations using a direct approach by energy minimization. Okay, but since I was interested in dynamics, I couldn't use a variational principle. I could use an Hamiltonian approach, but I decided to go another way and to use really standard tools from continuum mechanics, which is balance equations, integration by parts, and stuff like that. Okay, and this is the tools that I used. So here is the picture. So on the left-hand side, you have the shell in the reference configuration. Okay, S is the body surface. I fix a point X here, and Tx of S is the tangent space at point X, and it's the set of all vectors that are orthogonal to the normal n of X. Okay, this is the shell in the reference configuration. And now I developed I just used I just extended to surfaces the standard differential operators that we use in continuum mechanics. So you have, for example, the surface divergence. So the surface divergence is defined by taking the surface gradient of a vector field and contracting this with the projector. So the projector on the tangent space, which is the identity minus the normal dividing the normal. This is the projector on the surface. Then you can prove a divergence theorem on the surface. So if you take, for example, a part P, this part P of the surface, and you integrate the scalar product between an arbitrary vector field V, a tangential vector field V, and the normal field N is the normal field to the boundary of this part P, this is equal to the integral of the divergence of this vector field. And once you have defined the divergence of a tangential vector field, you can also define the divergence of any arbitrary tensor field, because you can write this tensor field, for example, as the dyadic product of a constant field phi with a tangential vector field, and you just say that the divergence of this guy is phi times the divergence of the vector field. And every tensor field can essentially be assembled by linear combination of objects of this type, and this gives you a definition of the surface divergence of arbitrary tensor field of whatever order, without using coordinate at all. And of course, a consequence of this is a divergence theorem for tangential vector tensor fields as well. Okay, and these slides summarizes the structure of the theory. Okay, so let me start speaking about the kinematics. So this is again the shell in the reference configuration. One important thing in this setting is that I consider the shell to be a body with oriented particles, which means that to each point I attach a director. And in the default configuration, so in the reference configuration, the director is perpendicular to the surface, but in the default configuration, the director D, which is this vector here, in general could be tilted with respect to the surface. So it's kind of independent with respect to the motion of the shell. Okay. So here, for example, you have the reference point is X. Y of X is the position of this point in the default configuration. This is the tangent space in the default configuration. This n bar is the normal in the default configuration, and this is the director. So you have these two fields. And why I introduce these two fields? Because I have balance of linear momentum, but also balance of angular momentum. And this gives me extra equations. So the balance of linear momentum is described by this equation, which, it's the standard one from continuum mechanics. So in this case, S is the Piola stress, B is the body force. So the superficial divergence of the Piola stress plus the body force is 0. This is quite standard. Again, capital F, using standard notation from continuum mechanics, is the gradient of the deformation. But for shells, you have something more. For example, you have this tensor field G, which is the gradient of the director. So it measures how the director changes from one point to another, and it's essentially a measure of bending. So bending is a measure of the change of the orientation of this director from one point to another. And associated to bending, you have another balance equation, which is this one. It tells you that the skew symmetric part of this tensor has to be 0. Okay, let's look at this equation. Here you see that another object appears which you do not have in the three-dimensional theory, which is this tensor field M. The tensor field M delivers contact couples, which are responsible for bending, which go along with the contact forces, which are described by S. So M is a sort of analogous to the Piola stress S, but it works for couples, okay? And so this balance equation, so this object here is a 3×3 matrix, which means that its skew symmetric part has 3 independent components. So if I, for example, if we consider a 3×3 matrix, so on the diagonal, you have zeros, and you can decompose the matrix like this, okay? Okay, before I comment on this, let me show you, let me make a remark about what happens when M is 0. So if the bending moment M was 0, and C here represents the external couples. So if this term was 0 and this term was 0, so what we would end up with is this condition. This condition says that the skew symmetric part of S, F transpose is 0, which is exactly the symmetry condition that you find in continuum mechanics, which reflects the balance of angular momentum. Okay, but for shells, this is more complicated because internal couples are also delivered by this tensor field M. And so you can imagine that it is the divergence of M somehow responsible for describing this density of couples. And if you want to count how many independent equation comes from this, okay, you have a skew symmetric tensor that has to be 0, so which means that you have 3 scalar equations. Out of these 3 scalar equations, essentially, there is this part that contributes to two independent partial differential equations for M. And this component gives you an algebraic condition that we will see shortly. Okay, once you have done that, for example, you may wonder what is the equivalent of the second Piola-Kirchhoff tensor. Okay, and the answer to this question comes from this formula that you see here. Okay, so if, again, if we were in three-dimensional continuum mechanics, and we wrote this equation, N would be the second Piola-Kirchhoff stress tensor, okay? But here you have an additional term, which is this one, and this takes into account shearing forces, okay? So I introduce this decomposition for the Piola-Kirchhoff stress tensor. Notice that another thing I want you to notice is that in this decomposition, you have two tensors whose range is independent, is linearly independent, because F is the deformation gradient. So this means that F, this capital F, maps tangent vectors in the reference configuration into tangent vectors in the deformed configuration. This second part of the tensor S, instead, maps again tangent vectors in the reference configuration to D, to vectors parallel to D. So it's really an orthogonal decomposition of this tensor. And you can do the same for all other tensor quantities. So you do the same for the bending moment tensor. So you introduce this decomposition here and here with this tensor product. And you do the same with the gradient of the director. Okay. And now if you do this, you can take these equilibrium equations And you can test them by a virtual velocity field, this one, and a virtual rotation field for the second one. So a virtual changes of position and orientation of the director. And you can do integration by parts. And this is how you get to the weak form of the equilibrium equation. This is what you teach to students. To obtain the weak form, you test by a field, the equations in strong form by a field, you integrate by parts, and then you have external power equal internal power, the principle of virtual work. Okay. And if you do if you play this game, you have the following. So consider so on the shell, you can consider an arbitrary part P. Okay, you consider an arbitrary part P. You test these balance equations by a virtual velocity and a virtual change of the director, and you integrate on P, within P. Then you integrate by part, and this is what you end up with. It's an identity where on the left-hand side, you have the power, the virtual power of external forces. So in particular, you see here, B is the body force, and B expends power on the virtual velocity Y. At the same time, the external couple C expends power on a virtual variation of the director D. Okay? And this is the essentially the power of external forces and couples. In this second term, we have an integral over the boundary of P. And this is the work done by the forces and couples that the complement of P exerts on the part P. So it's again external if you consider only the part P. And the interesting part comes here, because after some work, you can write down the internal power in this form. So you have three terms which measure the power expended over stretching, bending, and shearing. So, so if you look at this first term, so this n minus gm transpose comes from a combination of these three tensors, and essentially it measures what are the actions in the membrane part of the problem. And this object is power conjugate to the rate of change of this quantity E, which you can easily recognize. It's 1/2 F transpose S minus the projection. So this is a measure of stretching in the plane. It's a plane tensor. The second term is the bending moment, this part of the bending moment, multiplied by the rate of change of this curvature tensor, which is obtained by pulling back the gradient of the director to the reference configuration by P multiplication with F transpose. If you look at this tensor, look at just from the point of view of linear algebra, just to see the structure of this tensor. G is the gradient of the director, so it maps tangent vectors here into tangent vectors here, into vectors here. If F transpose, on the other hand, maps vector here into vector here. So this combination essentially maps referential vectors into referential vectors. So it's a purely referential strain measure. And it's a dual of this purely referential stress measure. This would be the equivalent of the second Kirchhoff stress. And finally, there is this term, which essentially measures how much the director phase should be orthogonal to the tangent space in the default configuration. And this can be easily seen because if the director D was orthogonal, if this vector D was orthogonal to the tangent space in the default configuration, then it would be orthogonal to the range of F, of the tensor F, and therefore it would be annihilated by F transpose. Okay, so when this guy is 0, it means that D is perpendicular to the director D is perpendicular to the surface. So this is a kind of extent. So as you can see, when you go from 3D to 2D, you have to add additional dynamical quantities, bending moments, and additional kinematics. But what is interesting here is that I do not postulate this measure of bending. So you find a lot of papers in the literature where people assume that the bending energy depends on this tensor, and then they develop their calculations. But in my case, I didn't postulate it. This comes just out from the calculations. Okay, so it's another motivation for using this as a bending measure. By the way, this is used, for example, in Coiter's theory of shells. Coiter uses that measure. Okay, and so since we wanted to study vibrations, what we did was to linearize those. Those are nonlinear equations. Those I was showing before are in principle nonlinear equations. So large deformations, large strains, and so on. But we want to study vibrations, so we linearize it. And we do this in the standard way. So we write the deformation as of a given point as the point plus a small displacement. And it's convenient to decompose this small displacement into a tangential and a normal part. So this V is the tangential displacement on the surface of the shell, and this W will be the orthogonal displacement. Okay, and of course you can also linearize the measures of strain. I mean, I can linearize this E, and I can linearize this K. Okay, and I will not have this term because in going from this slide to the next one, I'm introducing an assumption that the director will stay orthogonal to the tangent space in the default configuration, which means that I'm considering Kirchhoff-Love shells. Okay, the Kirchhoff shell, the director is perpendicular to the surface. And if you linearize epsilon, the stretching and bending measures, this is what you get. And if you have a look at this definition, for example, what is here is the superficial gradient of the normal in the reference configuration. Okay? Notice that when the shell is a plate, in the special case of a plate, this term vanishes, is zero, because the normal is constant. Okay? So for a plate, this is skilled. And what you find here, it's something very similar to what you have in linear elasticity. In linear elasticity, you have that the deformation is the symmetric part of the displacement gradient. In shells, there is something similar. You have a symmetric stuff. You have the symmetrization of the composition between the transpose, between the projector on the tangent space, and the superficial gradient of the tangential displacement. Okay. And the expression for the bending, it's a little more complicated, so I will not go into that. And these are the constitutive equations that are obtained from the linearization of the nonlinear constitutive equation. But I have to make a specification here. Now I'm thinking of really, I'm specializing the situation to the case where I have a spherical shell, and I am assuming that the linearization of the evolution of the balance equation is done in a pre-stressed configuration. Because the thing is that I want to study the vibration of the eye when the eye is pressurized. So which means that the reference configuration that I have to use is non-stress-free. It equilibrates the internal pressure, and this internal pressure generates a membrane tensor N, which is isotropic, which I denote by N dot. This N circle means the free stress. And people know that when you linearize the equations of elasticity in the presence of a free stress, it's not true anymore that, for example, the stress is symmetric. And there is this extra term, which is essentially a geometrical term, and that eventually it's responsible for the fact that the vibration properties of the eye, of the shell, depend on the internal pressure. So if you change the quantity here, this value, the dynamical property of the shell will change because you have changed the constitutive equations. And these are the equilibrium equations that you obtain. So this one is the equilibrium equation in the tangential direction. And this other one is the equilibrium equation in the normal direction. As you can notice, differently from theories of like 3D continua, the bending moment appears with a double divergence. So it's a second order equation for M, differently from the first equation. I mean, if you have seen the equations, for example, for Kirchhoff plates, you see that there is the double Laplacian. The double Laplacian comes from this double divergence. And of course, here you have a generalization because the surface is curved. So you have a curved geometry. So there are some extra terms. But in the case of a plate, all these extra terms that depend on the gradient of the normal will be here. And the equations will look very simple, of course. Okay, then how much time do we... Peak 5, okay. So, okay. Okay, I think that for mathematicians, maybe, I don't know about the previous part, but the next part may be a little bit boring because I'm discussing exact solutions for the vibration property of the eyebulb. So this is what I did. Essentially, I make an ansatz about the solution. And I assume that the displacement can be written as the real part of some exponential, which depends on time, times a vector field that depends only on position. So I'm doing separation of variables. This is what you teach to second and third year students. And the complex frequency here has a real and an imaginary part. Of course, the imaginary part here describes the frequency of vibration. The real part describes the attenuation of those vibrations. And I do the same also for the pressure increment. So there is a pressure increment inside the eyeball. So you will have pressure oscillations. And for the pressure increment, I assume the same representation. Okay. So what happens is that when I substitute this representation into the motion equations, the second time derivatives will be double multiplication by zeta. So for example, here, what I'm showing, those two equations are the equations of motions in the vitreous humor. The vitreous humor is the ball of radius r. So I'm really modeling the eye. Of course, the eye is not perfectly spherical, but we are approximating this with a spherical shell. So let's say a spherical shell of radius r. And within this R, I have the equation of motion of linear viscoelasticity. Linear viscoelasticity of an incompressible material. So I assume the vitreous to be incompressible. And this explains why I have this equation that tells me that divergence of the velocity of the displacement is 0, because you have isochoric motions. And this is why you have to account for this with a pressure Q, a Lagrange multiplier. And the motion equation instead has this form. So you have the first Laplacian times the complex shear modulus, G, which depends on the frequency, plus the gradient of the pressure, which comes from taking the divergence of the stress. And this term is the inertial force. So this would be second time derivative of the displacement. And this rho v is the mass density. So mass density times acceleration on the right-hand side. Okay, those equations are written inside the eye. So these are three-dimensional. And those equations are coupled with the equations that govern the motion of the eyeball, of the sclera. So you have to couple these equations with the shell on the boundary through appropriate boundary conditions. And those boundary conditions can be written in this form. So suppose that you take those equilibrium equations and you substitute the constitutive equations into this. So you get a set of partial differential equations in the variables in the unknowns v and w. Okay? And those hold at the boundary. So these partial differential equations essentially contain these terms. For example, for this equation, the first equation that I'm showing here is equilibrium of forces in the normal direction. So if you look at the left-hand side, sigma is the incremental stress, and sigma n is the traction that the vitreous is exerting on the sclera at the boundary. So just to explain, so here inside I have the vitreous, and the vitreous is exerting a force on the sclera. To compute this force, I have to take the normal. This is, let's say, minus the normal. I apply the stress tensor to this normal, and this gives me the traction, okay? The traction at the boundary. Then I project this traction again on the normal direction, and this gives me the force that the vitreous is exerting on the sclera. Okay, so the force that the sclera is experimenting from the vitreous, the normal part. The second term here instead describes the tangential force that the vitreous is exerting on the sclera at the boundary. Okay, these two forces. So the normal force appears in the equilibrium equation, in the motion equation of the sclera in the normal direction, this one. And the other term appears in the equilibrium equation for the motion of the sclera in the tangential direction. I'm not writing all terms. These terms, the terms I'm showing here account only for stretching. And they scale like the ratio between the thickness, h here is the thickness of the sclera, and r is the radius of the whole eyeball. So this is the aspect ratio, so the ratio between the thickness and the sides of the eye. And those terms take into account essentially stretching. There are other terms, the terms that account for bending, on the other hand, are higher order terms that scales like the third power of the ratio between the thickness of the sclera and the radius of the eyeball. Okay, it's a simple scaling argument because bending moments scale differently from stretching forces. Okay, again, P here is the intraocular pressure. This is the stress increment that I was showing here. And this G of Z, which appears in this equation, is the so-called complex shear modulus. So it has a real part that accounts for elasticity, essentially. And there is this other part with Z that accounts for dissipation. Okay? And these rho V and rho V and rho S are the density of the vitreous and the sclera. Okay, so the density of the sclera appears in the equations of motion of the shell. The density of the vitreous appears in the equations in the bulb. Okay, so it's quite elaborate, but in fact it's not difficult to. It's a problem not too much difficult to solve. So I would like you to compare these equations with what I was showing you at the beginning of the talk. Okay. So these are by the way, these equations all only for axisymmetric motions. The equations that I'm writing here, all for arbitrary motions. And you would agree that it's easier to understand the physics and the origin of different terms by looking at those in this case. And in particular, I want to point out your attention to the influence of P. The P that appears here is the intraocular pressure. So you can see that it appears in the same position as stiffness terms. So here mu and lambda are the Lamé moduli of the shell. And so a measure of stiffness. So the stiffness of the shell depends on the stiffness of the material and on the thickness, of course, the ratio between the thickness and the radius. And as you see here, the presence of an extra pressure is kind of equivalent to an extra stiffness. Okay, so it's a geometrical effect. Okay, so how you can solve this problem? Well, essentially you use spherical harmonics. This is a very well-known tool from mathematical physics. It's found, for example, in many in many books of mathematical physics, usually for for calculations in quantum mechanics, but also for other calculations. So the spherical harmonics are essentially the eigenfunctions of the Laplace-Beltrami operator, the surface Laplacian that appears in these equations, are the eigenfunctions of the Laplace-Beltrami operator in the sphere, on the sphere, and are classified using two indices, an index L and an index M. L is greater or equal than 0. L equals 0 corresponds to a constant function. And if L is greater than 1, you can have different spherical harmonics with this index M that ranges from minus L to plus L. And this is to the fact that you have different symmetries. I mean, they correspond. This is a complete system on it's a complete system on the sphere. So you can think of using this to for example, to represent whatever field you want. But since we are working with not with scalars, but with we are working with scalars. This W, the normal component of the displacement, is a scalar vector, but V is a vector, it's not a scalar. So you have to involve also the so-called vector spherical harmonics. So vector spherical harmonics are vector fields defined on the sphere. They are called usually P, B, and C. So the vector field P is essentially orthogonal to the surface. So suppose, for example, this X is a point on the sphere. So if I don't think I can erase it, would be. Okay. So if I'm on a sphere, and X is the position vector on the sphere, X divided by the norm of X is the unit normal. Okay. And so you can see that this P is essentially a field orthogonal to the surface. So it's used to represent the normal component of the displacement. In addition, you can define the vector B and the vector C. So the vector field B is defined by taking the gradient of Y, the superficial gradient of Y, which means that B is a tangential field. So B is normal. B is orthogonal. And finally, C is obtained by taking the vector product between the normal, X divided by norm of X, and B. So B and C are pointwise orthogonal. And it can be shown that this is also a complete system. The property of B and C is that B is curve-free, because it's the gradient of something, while C is divergence-free on the surface, because it's obtained by rotating the gradient of something. And so how do you represent the solution? As I said, I have two unknowns, the pressure increment Q and the displacement. So I write the pressure increment as a linear combination of spherical harmonics times some appropriate coefficients. And I do the same for the displacement field. Okay, so I represent this vector field in this way. And the fact that Y is an eigenfunction of the Laplace-Beltrami operator has the consequence that the equations for each mode are all decoupled. So you can study them separately. And the eigenfunctions and the eigenvalues will be, of course, different. Okay, now maybe I can discuss a little bit of this. So essentially, the vector field U is, of course, defined within the whole sphere. So those coefficients P, B, and C will depend on the distance of the point X from the origin. So norm of X here is the radius. So P, B, and C, this coefficient, the capital P, capital B, and capital C, will depend only on the radius, because we are studying a radial symmetric solution. And they obey, if you substitute this representation formula into the governing equations, you end up with a system of 4 ordinary differential equations for these coefficients Q, P, B, and C. They are all coupled. And you can solve these equations in terms of Bessel functions. And once you have found the solution, you have to impose matching conditions on the boundary. So the equation of motion of the shell on the boundary represent boundary conditions for this problem, homogeneous boundary conditions, which means that all equations turn out to be homogeneous. And in general, this means that the problem has only trivial solution unless you are at an eigenvalue. And the eigenvalue, zeta, is determined by solving a characteristic equation. So this is very standard. This is a very standard technique. You just consider the motion equations. You make an ansatz. You use let's say a complete system. You represent your solution through a complete system of eigenfunctions, and you find conditions for non-trivial solutions to exist. And those conditions actually are just written in terms of some algebraic equations whose roots you have to find. And in this case, you can find the roots numerically. Questions so far? No. Okay, so we wrote a MATLAB code to find those roots, and we compared the results with what we could find from a paper related to eye vibrations. So in this case, those authors did some experimental measurements, which they compared with a finite element code, and to calibrate the code and to verify that the code was doing well, they made experiment on rubber balls. So they took 25 millimeter rubber balls with 4 millimeter thickness. This is not an eye. This is really something made up just to make the comparison. So they consider a white water-filled rubber ball, and they found the resonant frequencies. And we made the same computation using their material moduli, and we found a reasonably good agreement. But you can notice that the agreement is better at low frequencies and is worse at high frequencies. And the reason for this discrepancy, I think, is because rubber, the Young modulus of rubber depends, in fact, on the pre-stretch. So if you change the pre-stretch, the tangential modulus will change, and this will result in an increase of the vibration frequency. I mean, you cannot do this using constant Young modulus. Constant Young modulus will not work on a spectrum of frequencies, because if you increase the stretch, you will have a different stiffness of the material. And in fact, this is quite relevant for the mechanics of the eye as well. But of course, I mean, this was just to check that what we were doing was fine. And okay, this is just for you to see how the vibration modes that we have found look like. There are essentially, for the lowest order mode, there are 3 vibration modes. The first one on the left, I think it cannot be seen very clearly, but here on the surface, there are this little arrow, and this arrow it's like, I can describe it's a twisting motion, okay? So the upper part of the shell is rotating in one direction, and the lower part is rotating in the opposite direction. Okay, so this is the first mode. The second mode, it's a mode where the sphere is kind of elongating on one axis. Okay, it's like this, it's going like this. And so you see that the vector field is pointing to the north in this part and to the south in the opposite part. So it's like squeezing, okay? And this is instead a breathing mode where essentially the ball is expanding and contracting, the last one, okay? Just to give an idea of these modes look like. And these are the modal shapes for, remember that the vector spherical harmonics depend on 2 indices, and the first index was L. So L equals 0 means constant motion, which means essentially expansion of the sphere, a uniform expansion of the sphere, which in our case is prohibited by the fact that the fluid inside the eyeball is incompressible, so the sphere cannot expand. And the second one corresponds to rigid motions that you can rule out. Okay, so the first mode that you have to look at is L equal to 2. The first index, and this index corresponds to three different types of motion. Okay, so these are the data that we took from the literature. So the radius of the sclera is about 11 millimeters. The thickness of the sclera is changing from one point to another. So the idea that you can approximate the sclera with a spherical shell of constant thickness is questionable. Okay, so it's kind of problematic. So our idea was to replace the Young modulus of the sclera with an effective one, a sort of homogenized Young modulus, in a way that we thought a regular sphere would behave like an homogeneous eyeball by an appropriate choice of the Young modulus. And to do that, we resorted to a notion that had been introduced quite a long time ago by Friedenwald in 1937. So Friedenwald in 1937 was doing the first studies on the mechanical properties of the eye, and he came up with a concept of ocular rigidity. So to define and to measure ocular rigidity, he made experiments where he was taking samples of the eye, ex vivo, of course, and he would pressurize the eyes, and he would measure the volume contained in the eye. This can be done quite easily. And he found that no matter what the pressure and the volume were, he found that the relation between the internal pressure of the eye and its internal volume was very well described by this empirical law, where K could be taken to be a constant. This is not real at all. Okay, it's not guaranteed. But somehow he found this result. And he made an estimate. So this is essentially a pressure volume curve, like a gas, but for the eye. And it's a measure of the stiffness of the eye, because, of course, the greater is K, the greater is the pressure corresponding to a given volume. This is why it's called ocular rigidity. So this strange relation looks fine. And by using this relation, we have been able to estimate what should be the value of the incremental Young's modulus of the eye that we should introduce in our equations to have a sort of homogenization. So the idea is that you make a global measurement of the global properties of the eye as far as stiffness is concerned. And from this global measurement, you can infer what is the effective kind of Young modulus that you should use in your calculations. And this effective Young modulus will sort of average over all different thicknesses of the shell to give a homogenized shell, an effective material property. Of course, this formula is supposed to hold for pressure that are relatively high, so in the physiological range. So they don't work for zero pressure. But what you see here is that the Young modulus of the eye, the effective Young modulus of the eye from experiment turns out to be proportional to the pressure. And the reason for that is very simple, is that biological materials, if you look at the stress strain curve, sigma epsilon, okay, the stress strain curve of a biological material, this curve exhibits a strain stiffening, which means that the more you load the material, the higher is the tangential Young modulus. So the Young modulus is the tangent of this curve, is the incremental material modulus. The more you stretch the eye by applying more pressure, the more you move the system to the right, and this increases the stiffness. So in these equations, in the equations that we have to solve, the pressure does not come only through this term, which is geometrical, but should also affect these terms. So this should be constitutive. Okay? There is a double effect. Okay, so these are this figure shows the result of the calculations for different types of fillers. The reason why we are considering this is because maybe some of you know that in some cases, when you make a surgical intervention to the eye, you have to remove the vitreous. You have to take it away, and then you have to substitute the vitreous with some type of filler. And doctors have tried all kinds of stuff, possible stuff, and they came up with. They found that essentially silicone oil seems to be the best substitute for the vitreous. So what you see in this figure is these are the eigenvalues of the system. So for example, for the vitreous, you have one eigenvalue is here, one eigenvalue is here, and one eigenvalue is here. Okay, no, they are superposed. The first eigenvalues for the vitreous is here, the second here, and the second here. So on the horizontal, you have the damping rate, and on the vertical, you have the frequency of oscillation. And so you see that the lowest mode has a very low damping, and this is the mode that you should be focusing on, because the other ones will just decay very quickly. And what you see is that now you understand why silicone oil seems to be so good as a substitute, because essentially it doesn't change much the damping characteristic of the vitreous. So it's a very good substitute. And what else? Okay, so and now you can also see what are the frequencies. The lowest frequency that we found was something around 200 hertz, more or less. And this figure, in the other end, is showing the dependence on the resonant frequency of the mode with the lowest damping, the one that is more relevant, depending on the intraocular pressure and on the ocular rigidity. I mean, we wanted to see what was the effect of ocular rigidity on the dynamical behavior of the system. So we tried 3 different values. And what you see is that this figure suggests that it's really possible to measure intraocular pressure by looking at the vibration properties, because there is a sensible dependence of the vibration frequency of the pressure. So in principle, you can do that. If you increase the pressure, the vibration of the lowest mode will change, and you can detect it. And what is also interesting is that if you, instead of plotting these curves like this, you use a log-log chart, those will stand on straight lines with which are parallel, okay? Parallel lines. And of course, if you increase the ocular rigidity, you can see from this picture, the vibration frequency will increase. This can be expected. Another thing that you can do, you can question whether considering the strain stiffening due to the increment of pressure is really important to evaluate the vibration properties. And this you can do by plotting 2 curves. The first one is obtained by letting the Young modulus change. So taking into account that you have stiffening due to the increased pressure. And the blue curve here is what you obtain if you keep the Young modulus constant. So you do not take into account this kind of stiffening. And what you notice is that the sensitivity is much smaller. So which suggests that this strain stiffening effect, which is typical of biological tissues, is crucial for the measurement. And also here, we wanted to do a sensitivity analysis of the resonant frequency. So for a given, we wanted to measure for a given intraocular pressure, and for a given K, the values of constant frequency. So you see from this picture that for low intraocular pressures, the curves where you have the same damping rate do not depend much on the ocular stiffness. So ocular stiffness seems to be not so much important to the system is not sensitive to ocular stiffness for a small range of frequencies. This is for the lowest decaying mode. And well, I think I can stop here. This is a summary of what we have done. So we have developed a mechanical model for the vibration of the eyebulb. The cornea and the sclera are modeled as a thin elastic shell with pre-stress. The pre-stress is due to the intraocular pressure. And what is important is that differently from what you find in the literature, the model takes into account the effect of pre-stress through a consistent linearization. So it's not introduced ad hoc, the effect of pre-stress. We have solved all these equations in a series expansion using spherical harmonics, a complete system. And essentially, we have found the relation that you have between pressure and vibration frequency of the lowest mode, which in principle can be used for building a device that you could use to detect changes in intraocular pressure. And thank you for your attention. And let me advertise these two papers. The one on the application is has appeared on PLOS ONE. It has been published last month. And the theoretical paper on which this is based has appeared on Mechanics of Materials, and you should look there if you want to have more details about the shell model. Thank you for your attention.